Moving on to the next section, we are going to be talking about curves in space, and vector-valued functions help describe them. So if you remember back to two dimensions, when we have a plane where we have an x-axis and a y-axis, any curve on that plane can be described as a function or any equation involving x and y. Most of the time, it's y as a function of x, where x is the independent variable and y is the dependent variable. So let's say we have a curve going through 3D space. We have a vector r of t that starts at the origin, and its terminal point is a point on the curve. The point that r of t points to on the curve has an x, y, and z position, and those positions are described by the functions f of t, g of t, and h of t. So in this case, t is the independent variable, and each position, x, y, and z, are dependent variables. And whenever we change the value of t, we have new vectors pointing to different points along the curve. So like before, these vectors can be described in component form or in vector notation. You may notice that this is similar to describing lines in space, but for that case, f of t, g of t, and h of t are all linear terms. And for curves in space, the functions can be anything. Let's review the parameterization of a circle with a radius of 1 in 2 dimensions. So for 2 dimensions, we have a plane, an x-axis, and a y-axis. To form a circle, we have x squared plus y squared equals the radius squared, and the radius is 1. So if we wanted to parameterize it, we would need to use the independent variable t. Remember, sine squared plus cosine squared equals 1. So we can say that x equals r cosine t, and y equals r sine t, and r, the radius, is 1. So we can just make the substitution. So we can have this vector equation. Vector r of t equals cosine t, comma, sine t. First, we have the equation in terms of both positions, x and y. We know how to plot a circle. We can create a table for t, x, and y, so we can know what the values of x and y are whenever we change the values of t. We'll start by plugging in a 0 for t. The cosine of 0 is 1, and the sine of 0 is 0. So that means we have a vector starting from the origin, and at t equals 0, we're going to the point 1, 0. If we try t equals pi over 4, r of pi over 4 equals cosine of pi over 4, which is square root of 2 over 2, and sine of pi over 4, which is also square root of 2 over 2. So the point the vector r of pi over 4 points to is here. So we can keep increasing values of t, and once we get to t equals 2 pi, we would have revolved around the circle once. And as values for t increase, points keep going counterclockwise around the circle. So for parametric equations, there's an orientation to the curve, and we can label them with the arrows like this. If you swapped x and y, where x equals sine of t and y equals cosine of t, the orientation would be clockwise. Let's take a look at a 3D vector function, r of t equals cosine t, sine t, t. This means x equals cosine t, y equals sine t, and z equals t. The first thing we want to do when we want to plot a curve in space is to find an equation involving two of the dependent variables. So since sine and cosine are functions for two different components, we can make the same relation again. Substituting this for the dependent variables, we have x squared plus y squared equals 1 is a circle, but since we have two variables in a 3D space now, we're going to have a circular cylinder. So we can do the same thing where we increase the values of t. So we can plug in 0 for t first. So r of 0 equals cosine of 0 equals 1, sine of 0 equals 0, and then it's just t, which is 0. So the first point at t equals 0 is at 1, 0, 0. Next, let's plug in pi over 2 for t. We'll get 0, 1, pi over 2. We'll have a point at 0, 1, pi over 2. So when x is 0 and y is 1, we're here, but we're going up pi over 2 in the z. And then we can have a point up here. And then for r of pi, we'll have negative 1, 0, pi. So this point is going to be located on the back edge of the cylinder. And then we could see that this is the path of the curve. Now we could label the orientation as well. So this curve is a spiral or a helix. If you look straight down the cylinder, this would be the motion for the xy direction. It's the same counterclockwise motion. And then we could do the same for x and z and y and z, but these are not necessary. So since z equals t, we can make a simple substitution into the x and y functions, and then we could easily plot these. So looking straight down the z-axis, we would see the curve along x and y, and we'll see that it's in a circular shape that goes counterclockwise. If we look at it from either of the sides, we'll see that the curve looks like a sinusoid going up. So basically what's going on here is that as t increases, it goes around counterclockwise, but since z equals t, it also moves up. So that's how we have the spiral or helix created. Also, instead of the circular cylinder, we could have plotted any of these two as well. X equals cosine of z and y equals sine of z are both cylinders, since they have two of the three variables in it. And regardless of which two variables you use to get your equation, you should have some sort of cylinder, and the green curve given by r of t would always go along that surface. When it comes to taking the limit as t approaches a value a for your vector function r of t, you're essentially just taking the limit as t approaches a for each of the component's functions. And the domain for r of t is the intersection of the domains for f, g, and h. That means a value of t must be able to exist in all the component's functions if it is in the domain of r of t. We'll do some examples covering both of these. Okay, so for example 1a, find the domain of r of t equals t squared plus 1, t to the negative 1, and t to the half. We can rewrite r of t as t squared plus 1 we could keep the same, and then t to the negative 1 is 1 over t, and t to the half we can say is the square root of t. So for the first component, we have t squared plus 1. That is a polynomial, so all real numbers are in the domain. In interval notation, we can say the domain is from negative infinity to infinity. And then for 1 over t, t cannot equal 0. In interval notation, we can say this is from negative infinity to 0 exclusive, union 0 to infinity. For square root of t, t just needs to be greater or equal to 0. Or you could say in interval notation, bracket 0, comma, infinity, parentheses. Let's take a look at a number line. The domain of r of t is the intersection of the domain of the functions for each component. First, the domain for t squared plus 1, since it's a polynomial, it's all real numbers. The domain for 1 over t is all numbers except for t equals 0. So if this is 0, we can have a hole right here, and then we have all numbers going to the left and all numbers going to the right. And then finally, the square root of t, t must be greater or equal to 0. So the domain would start at 0 and include it and go all the way to the right. If we wanted to find the intersection of the domains for all three functions, we need to look at where values of t could apply for all of them. So that means that the values for t that we can have in R of t must be greater than 0. So that means we could say the domain of R of t in interval notation is parentheses 0, comma, infinity, parentheses. We can't include 0 because of 1 over t, and we can't have negative values because of the square root of t. Let's do part B. Find the domain of R of t equals sine of t, ln of t, and 1 over t minus 5. The domain of sine of t is all real numbers, so we can say parentheses negative infinity, comma infinity, parentheses for interval notation. And then the domain of ln of t is t is greater than 0, or this in interval notation. For 1 over t minus 5, t can't equal 5. So this is the domain in interval notation. Negative infinity to 5, exclusive, union, 5 to infinity. So for sine of t, the domain is all real numbers. We don't need to restrict anything. For ln of t, all t values must be greater than 0. So if this is 0, we are looking at every value of t greater than it. And then for 1 over t minus 5, it's all real numbers except for t equals to 5. So again, the domain of R of t is the intersection of the domains of all the functions. So that means the domain of R of t is for t values greater than 0 and excluding 5. Okay, so for number 2, find the limits. For part A, find the limit as t approaches 1 of R of t if R of t equals arc cosine of t, comma, t cubed minus 1 over ln of t, comma, square root of t plus 1. Okay, so there is a limit for R of t if the limits of each component's functions exist. So to find the limit, we'll need to take the limit across each component's function. First, we'll take the limit as t approaches 1 of arc cosine of t, or the inverse cosine of t. We could just find this by direct substitution. So plugging in a 1 for t, we'll have the arc cosine of 1, which just equals 0. Next, we can take the limit as t approaches 1 of t cubed minus 1 over the ln of t. If we try direct substitution, we'll have 1 cubed minus 1 over the ln of 1, which gives us 0 over 0, and this is indeterminate. And since we have 0 over 0, we can use L'Hopital's rule. We can rewrite this as the limit as t approaches 1 of the derivative with respect to t of t cubed minus 1 over the derivative with respect to t of ln of t. Now we have the limit as t approaches 1 of 3t squared over 1 over t. And now we could directly substitute. And then for the limit of the last function, we could do a direct substitution for that as well. I'll get the limit as t approaches 1 of the square root of t plus 1 equals the square root of 2. So since the limits exist for all of the components' functions, we can say the limit as t approaches 1 of R of t equals the vector 0, 3, the square root of 2. For example 2b, we're finding the limit as t approaches 0 of R of t if R of t equals sine of t over t, the exponential of t minus 1 over tan of t, and 2t over sine of t. So again, let's take a limit as t approaches 0 for each of the functions. So starting with sine of t over t, if we try directly substituting, we'll get an indeterminate form. We could apply L'Hopital's. Now that we took the derivative of the numerator and the denominator, we can directly substitute. Now let's take the limit for the second function. Directly substituting gives us an indeterminate form again, so we can try L'Hopital's again. And now after we take the derivative, we can directly substitute. And finally we'll do it for the last function. We'll also get 0 over 0, which is indeterminate if we try directly substituting. So we can try doing L'Hopital's for this one again. Alright, so now that we found the limits for each of the components function, and they all exist, we can say that the limit as t approaches 0 of r of t equals 112. For number 3, sketch a surface and a curve on the surface with orientation for r of t equals the square root of t plus 2i plus 2tj plus 2t squared k. So this is in ijk notation. If you want to put it in component form, you can. So based off the vector function, we have x equals the square root of t plus 2, y equals 2t, and z equals 2t squared. So first, we want to find an equation that involves two of the dependent variables, so any two of x, y, and z. And if we have two of the three dependent variables, we can have a surface, which is a cylinder, and our parametric curve is going to go on that surface. So an easy substitution we can make is isolating t for the y equation. So we have t equals half times y, and then we can plug this into the z equation because we know what a parabola looks like. Now you can isolate however you want, and you can substitute any of the variables you want. For simplicity, this is an equation of a parabola. I'm going to substitute t into this equation. So we have z equals 2 times 1/2 y squared, and this is z equals 1/2 y squared. And then this is a parabolic cylinder, and we can graph that on the 3D graph. Okay, so the curve for r of t is going to be along the surface somewhere. One of the functions has a square root, and there's a t plus 2 in the square root, so that means the domain is values of -2 and greater. So next we can start plugging in values of t to get some points. So we can start with -2. Plugging in t equals -2 gives us 0, -4, and 8. So let's just say that this is where 0, -4, and 8 is. And then we can increase the values of t. Let's say t equals 0, we'll have the point square root of 2, 0, 0. And that's going to be somewhere on the x-axis. Then we can plug in a 2 for t, and we're at the point 2, 4, 8. And now we're on the right side of the parabola somewhere. So you can make out a curve like this, and we can put on the orientation arrows towards the greater t values, and that curve is always going to be along that parabolic cylinder. And looking at the equations and the graph, you may notice that when you increase t, x also increases, but less each time, like a square root, and y increases linearly with it, and z initially when t is -2, z decreases, and then after t equals 0, z increases again, like a parabola, and that is how you sketch a curve given a vector equation. I plotted the 3 points we found, and the curve given by r of t on Desmos, so we can look at it from different perspectives. And the surface of the parabolic cylinder, z equals 1/2 times y squared. You'll notice that the curve of r of t, which is the purple, is going to always be on this parabolic cylinder. For number 4, sketch a surface and a curve on the surface with orientation for r of t equals 2 sine of 2t I plus t squared j plus cosine of 2t k. Based off the components, x equals 2 sine of 2t, y equals t squared, and z equals cosine of 2t. And then we can create a surface in the space that the curve will be on by making an equation with two of the dependent variables. So since sine and cosine are on different component functions, we can make the sine squared plus cosine squared equals 1 relation again. For the x equation, we can isolate so that sine of 2t is by itself. X over 2 equals sine of 2t. Substituting the t for the x and a z, we'll have x over 2 squared plus z squared equals 1. And then this is x squared over 4 plus z squared over 1 equals 1. And if we have an equation with two of the position variables in 3D space, we will have a cylinder, and this equation is of an ellipse. So we'll have an elliptical cylinder. And this wraps around the y-axis. So the elliptical cylinder is what the curve is going to be on. Looking at the functions, the domain of r of t is all real numbers. So we can start putting in values for t to plot points. Plug in 0 for t, we'll have the point 0, 0, 1. This is going to be on the z-axis, and it's just going to be the top of the ellipse here. For t equals pi over 4, we'll have the point 2 pi squared over 16 and 0. So we'll move positive along the y-axis by a little, and then the point will be on the left side of the ellipse. For t equals pi over 2, we'll get the point 0 pi squared over 4 and negative 1. And that's going to be on the bottom of the ellipse. For t equals 3 pi over 4, we'll have negative 2, comma 9 pi squared over 16, comma 0. And then for t equals pi, we'll have the point 0, pi squared, and 1. So connecting the points, we can make out this curve. The curve is a spiral that goes around the cylinder. Here are the points and the curve we just found on Desmos. So at t equals 0, we have the blue, and then increasing values of t, we go along the curve towards the positive y direction. And then you can see the curve spirals around, and if you look at it down the y-axis, it's the ellipse. So in blue, this is the elliptical cylinder, x squared over 4 plus z squared over 1 equals 1. And the red curve for r of t is on it. But since the domain is all real numbers, we can also have negative t values. And as we go more and more negative for t, we're going along this curve. Number 5, find the points of intersection between the curve r of t equals t 2t t squared and the quadratic surface x squared plus y squared over 4 equals z squared. So from the last video, we are able to identify that this quadratic surface is an elliptical cone. And then from the component functions of r of t, we can say that x equals t, y equals 2t, and z equals t squared. So r of t describes the curve, and if we change values for t, we'll have different points on the curve, because x, y, and z are the positions of the point. If we substitute x, y, and z out for functions of t, we can find the values of t when the intersection occurs. So let's rewrite the elliptical cone equation with the variable t only being in there. So x equals t, so instead of an x squared, we'll have a t squared, plus y equals 2t, so we have 2t squared over 4, and then equals z equals t squared, and z is squared, so we'll also square this. And now we have the quadratic surface expressed in t. And we can simplify. After combining and rearranging some terms, we can get t to the 4th minus 2t squared equals 0. And now we can factor out a t squared and solve for t. So the curve r of t intersects the elliptical cone at t equals 0, t equals radical 2, and t equals negative radical 2. We can take these three t values, plug it back into the r of t equation, to find out the 3 points of intersection in terms of x, y, and z. So for t equals negative radical 2, the point we're going to get is negative rad 2, negative 2 rad 2, and 2. For t equals 0, we're going to have 0, 0, 0. And for t equals rad 2, we're going to have rad 2, 2 rad 2, and 2. So these are the 3 points when the curve intersects the elliptical cone. If you want to get a visual of what this looks like, we can plot it on the 3D graph. So first we have the elliptical cone. I'm not going to be too exact with it. And then for the curve, we can get the surface that the curve is on by having an equation in terms of 2 of the 3 dependent variables. So first we can get an equation with x and y and with x and z, since x just equals t, and we can just make a direct substitution. We can have y equals 2x and z equals x squared. And if we want an equation with y and z, we can isolate for t in the y equation, and then we can plug this into the z equation, and we'll get z equals 1/4 times y squared. This one right here is a plane, and then the other two equations are parabolic cylinders. So the curve for r of t is going to be found on each of these surfaces. But for graphing, we can just choose any one of these equations. I'm going to choose z equals 1/4 times y squared, because for me, I think it's easier if we have the cylinder that goes down the x-axis to draw. Again, I'm not going to be super exact, this is just to get an idea. Now let's plot these points, and of course, these points are going to be on the surface of the parabolic cylinder. So first, at t equals negative rad 2, we have negative rad 2, negative 2 rad 2, and 2. So with a negative x and y value and a positive z value, it'll be somewhere along the back left. And then at t equals 0, 0, 0, 0 is at the origin. And then at t equals rad 2, we have rad 2, 2 rad 2, and 2. So with all positive values, it's going to be in the front and on the right. If you want, you can put in more values of t into r of t so you can get more points. The curve is going to look something like this. And then I'll also show you on Desmos. So here's the curve for r of t equals t 2t t squared. And of course, this is on the surface of the parabolic cylinder we found. Z equals 1/4 times y squared. And just to demonstrate, it could also be found on the other two surfaces. We had z equals x squared, the other parabolic cylinder, and then we also had the plane, y equals 2x. So what you see in blue is the elliptical cone, and here are the 3 points of intersection between the curve and the elliptical cone. First, at t equals negative rad 2, we have the point negative rad 2, negative 2 rad 2, and 2. And at t equals 0, we had 0, 0, 0. And at t equals rad 2, we had rad 2, 2 rad 2, and 2. And these are the 3 points of intersection when the curve intersects the elliptical cone.